All right, so we're going to talk about a factorial experiment. So if I have a variable, if I have two different variables, right? Like, let's go back to my running example. Let's say I want to see how the temperature and music impact my run. So if I have two factors, how many combinations of those two factors exist, right? And let's say I use music, the loudness of the music, to make it something like that. How many combinations of those factors are there? Well, the answer is there's infinite factors, right? There's infinite temperatures that you can have. There's infinite loudness to the music that you can have, right? So there's quite a few. So the first thing that we attempt to do when we're creating a factorial experiment is, if we look at these two variables, right? We'll take music here, and we'll take temperature here. What we attempt to do is we attempt to set a high level and a low level of each factor. Now we're going to assume that we're inside a room, so we can set the temperature thermostat of the room. Maybe we're running on a treadmill in this particular case, so we can see these factors. So there is a setting where we have low volume music and low temperature, low volume music and high temperature, high volume music and low temperature, and high volume music and high temperature. And so it creates this kind of box, right? So let's say I'm going to run 2 miles and I'm going to record the times. And I did this at 9 minutes, and this was at 7 minutes, and this was 8 minutes, and this was 11 minutes, okay, for those time frames. So how do I analyze the data from an experiment such as this? Well, the measurement of an effect, right? How much does a factor have an effect on the output is going to be equal to the average of the high minus the average of the low. That's how we would measure the effect, essentially the coefficient on what's happening here. So for temperature, let's look and see what is the impact that temperature has on this process. Well, the average of the high would be when the temperature is high, so that would be 9 plus 7 divided by 2. And then the average of the low would be 11 plus 8 divided by 2. And that's going to end up equaling negative 1.5. Okay? And so if I look at the effect of music, that would be the average of the high, so that would be 7 plus 8 minus, when music's low, 9 plus 11. And so I end up getting a value of negative 2.5. So that's telling me that music has a higher impact on runtime than temperature, right? Where the louder the music is and the warmer the temperature is, the lower the runtime is. That's what the negative coefficient is telling you. Well, I told you that there was this interaction effect. So how do we test the interaction? Well, it's the same way. But if you think about it here, if I have a high, let's call that a positive, and so let's call this as the high, and I'll indicate that with a positive, and the low is a negative and positive here. Then when you have a positive and a positive, that's a positive. When you have a negative times a negative, that's a positive. And when they're different, they're negative, right? So that is how we measure the high and the low. So when would the multiplication of these two factors be positive? Well, when you have both positive, that's a 7. When they're both negative, that's 11. And then the value at the low is when they're different. So that would be the 9 plus 8. And that difference is going to be 0.5, right? So the interaction effect between the two of them is much smaller, meaning that the effect that they're going to be behaving differently with different levels is lower. Okay, so I'll make a note here. Note, with n data points. Okay, with n data points, right? We can estimate n minus 1 factors. So like one of those factors becomes a reference point that you're using, right? So, you know, if I have 4 data points, it allows me to estimate 3 factors. Notice that's music, temperature, and the interaction between music and temperature. And I'm out of factors that I can estimate. Okay? So as I was saying, we often choose a high level and a low level, and especially for continuous variables, what that's allowing us to do is quickly determine, is that factor significant or not significant? Now, it kind of assumes, doesn't fully assume linear, but it assumes that if you don't see a difference at 2 levels of the factor, one high and one low, then that factor is probably not impacting the output variable, and then you can discard it from further consideration. You might want to hold it constant just to have some experimental consistency in case there's a little bit of an impact, but generally you assume that it's just not impacting it, and so you don't have to consider it in further analysis. Okay, and so what we do is we then talk about it in 2K factorial combinations. So that 2 is getting the idea that there's a low and a high level. The K is how many factors you have. So right, we can make a little table and we can say for a given K, number of factors, how many number of experiments would you need to be able to understand how all of those factors and their interactions are impacting the space, right? Well, we can create a little table here, and if there's 2 factors, then 2 to the 2 is 4 experiments. That's what we saw here. If, however, I have 3 factors, I now need to do 2 to the 3rd or 8 experiments. If I do 4, I need 16. If I do 5, I need 32. All the way up to, if I'm going to do 10, I need 1,024 experiments. Well, you can see that that's going to get really big really quick as you start adding additional factors. So surely there's a way that we can do something a little bit more clever. And one of the benefits we're going to do with statistical design of experiments is we are going to choose combinations in a clever way to reduce the number of experiments. Okay, so how does that work? Well, at this point, what I'd like to do is just do a quick review of what we would do before we choose the reduction of experiments here. So we'll come back to this in a moment. Okay, so if I have one factor and one level of the factor, right? So one factor and it never changes, right? So I just have, I'm going to use the music is the only factor, and I just keep it at the same volume the whole time, right? What are my options? Well, the things that I have to understand this factor is I can look at the average response, and I can do that with the formula of I equals 1 to n variables of all of those items divided by however many there are. I can also look at the variance, and so that is going to be I equals 1 to n. That is going to be my value for y minus the average squared over n minus 1, right? And those are the options that I have. If I have one factor and 2 levels, right? So now I have 2 levels of the variable. What is available for me? Well, now I can do something called a t-test. And the t-test is going to basically take the variables at one value, or one level loud music, the variables that were taken at the low level, and see, hey, there's two different distributions here. Do they overlap? Are they telling you the same thing, or are they different, right? It's basically saying, hey, are these things the situation where my distribution looks like this, and they're like just a little bit different, or does it look like this, where they're very different? And so it's saying, taking this hypothesis that the mean of one is equal to the mean of the second variable, which can be also written as mean of 1 minus mean of 2 equals 0. And so what that allows me to do is create a t-statistic, and that t-statistic is going to be the average of the first sample minus the average of the second sample. And then what we are going to do is divide that by a weighted average of the variance. So we have n1 minus 1 times the variance of 1 plus n2 minus 1 times the variance of the second sample divided by n1 plus n2 minus 2. That's going to give me my t-statistic. And then I'm going to test the t-statistic against a reference distribution where degrees of freedom equal n1 plus n2 minus 2. Right? So when you go into R or Excel even, and you're going to actually test this, you need to know what the degrees of freedom are for the reference distribution, and then the test statistic you calculate here. And what that's doing is it's saying if in fact there is no difference between these two distributions, that t distribution should follow this pattern centered at 0. And if I see a value in here, then I'd be like, hey, there's nothing wrong with that. But if I see a value out here, for example, then I'm going to say, I don't believe that this value came from this distribution. Therefore, this assumption might be wrong. And the way we do that is we take the area under the curve, and that area under the curve is called a p-value. And if it's very, very small, then the smaller it is, the further in the tail it is, the less I believe it. Okay, so that's what we're going to do if we have one factor and two levels. Okay, what happens if we have one factor and three levels? If we have one factor and three levels, right, then we're going to apply something called the analysis of variance. Okay, and the reason for that is if I just did a t-test and there was a 5% chance of making a mistake, right? That means it's 95% likely to be correct. So let's say I tested 8 combinations of those variables. Like I had 3 factors, I'm testing 8 combinations to see if any of them are different. Well, that would be like 0.95 to the 8th power, which ends up resulting in a 34% chance of error. And you can work that math out if you like. So what ends up happening is as we have more and more combinations to test, we're compounding the likelihood of making a mistake, and that can be problematic. So the way we get around that is we look at the overall variance. And so let's say I have 3 different levels. So I now have music at this center value here as well. So I have 3 different levels. And so I want to test if there's anything different between them. So I analyze the variance. And so I'll move up here. So when I'm doing something called ANOVA for the analysis of variance, right, I first want to look and see, well, what is the variance that happens between levels, right? What is the variance that happens within a level? And then what is the total variance? And so the total variance would then describe like all the different run times that you've had. So then I can say, well, I can look and see how much are the variance within high loud music, medium music, and quiet music, right? I can look at those individual variances within each of those categories. And then I can see, well, what about the average here, the average here, the average here? Does it vary between the levels, right? Not just within the levels. That's what we mean. So to do between the levels, right, we would call that sum of squared L. And what that is going to be is I'm going to take n, right, N in this case is the number of samples, or the number of levels. And so I'm going to say sum between I equals 1 and A. That's how many data points are in, how many levels that we have, right? How many levels that we have. And so we're going to then take the average of all of the points within the level, and we're going to subtract that from the overall average of all of the data points, and we're going to square that. Notice it looks very similar to the top part of the variance equation because it is, right? But what we're doing is we're taking the difference of the average at each level. So it's basically saying, how does the average of each level, what's the variance of those averages for each level? Okay, and that's what we're going to call the sum of squares for the levels. And then for within the levels, we're going to come back to that for a minute. The sum of squares total is simply the variance of the overall data of all the runtimes. And the way we write that, you'll often see it written as I equals 1 to A, for the number of levels. Sum of j equals 1 to n for the number of observations within each level. And so that is going to be each data point minus the overall mean, right? That's the same thing that you would just do here for all of your data, okay? That's the sum of squares total. And then to get the sum of squares error, so this is the amount of variance that's now not explained by these three different levels. That is simply going to be the sum of squares total minus the sum of squares level. Okay. Now, what we end up doing is we also have degrees of freedom, right? How many data points do we have here? And so the degrees of freedom that we have here, right, for each of these is A minus 1. So however many levels, if you have 3 levels, you have 2 degrees of freedom. At the total degrees of freedom is however many data points you have minus 1. And then what you have here is n minus A degrees of freedom there. And so the way we analyze this is with an F statistic. And the F statistic is going to be the sum of squares of your levels divided by the degrees of freedom for that, which is A minus 1. And the sum of squares, the bottom here, is your sum of squared error. And that's going to be divided by n minus A. And this will give you an F statistic which follows a distribution that's a little bit more skewed. But the same thing is going to happen where you're looking to see, are you way out here in this tail where you have a very, very teeny p-value, in which case the hypothesis, right, which is the variance of 1 equals the variance of 2 equals the variance of 3, right, that they're all the same. That hypothesis, if that's true, then this number will follow a distribution like this. If it's way out in the tail, then I do not believe that distribution, and it tells me at least one of them is different. Now I can use my t-test to figure out which one is in fact different. Okay, so then what happens when I have my last condition where I have, if I have 2 factors, each at 1 level, well, that's the same problem as 1 factor at 2 levels. It's kind of semantics, right? Factor level. But if I have 2 factors and I have 2 levels, this is where we're going to now try and do a factorial design. And in the factorial design, what we're going to attempt to do is be a little bit more clever in the way that we construct this. Okay, so the next video is going to tell you how we actually conduct a factorial experiment and how we design it and how we use this clever way to reduce the experiments. But what I want you to take away and take a really important note on is, if you have, right here, if you have one factor, one level, you're just going to take descriptive statistics. If you have one factor and two levels, you're going to do a t-test. If you have one factor and three levels, you're going to do an analysis of variance followed by the t-test to see what's different. And if you have two factors or more, and each of them at least two levels, then you're going to start doing factorial experimentation, and you're going to want to design a clever subset so that you can reduce the time wasted in your experimentation and lower the cost.